So now, when we have this material evaporating, we have vapor or a gas, and it has a certain pressure. And we talk about vapor pressure. It's the pressure exerted by the vapor of a liquid. The equilibrium vapor pressure is the vapor pressure we would have in a sealed container when we've reached equilibrium, and the material is evaporating and condensing at the same rate. The equilibrium vapor pressure is the number found in the tables. Now, we talked about this in the gas law chapter. Remember when we talked about collecting water or collecting gases over water, and we subtracted out the vapor pressure of the water? That's what this is. So the vapor pressure depends on the temperature of the liquid, and it's based on the rate of evaporation per unit area. So the vapor pressure over a pie plate or a bud vase would be the same because we're compensating per area. It's force per area. And as the temperature increases, vapor pressure increases. As intermolecular attractions increase, vapor pressure decreases. Because as intermolecular attractions increase, fewer molecules are evaporating. They're all holding on to each other. So why am I drawing these lines on the board? Because when we get to the evaluation for this unit, the test, you're going to be asked to look at a series of materials. And there will be a list of formulas. At this point in the semester, it's your job to pull together everything we've done. You have to look at that formula, think about it, say, okay, I'm going to draw the Lewis structure, then I'm going to think of the molecular shape, then I'll decide, does this have dipole forces? Is this a polar molecule? Is it a nonpolar molecule? Does it have hydrogen bonding? You'll decide what kinds of intermolecular forces you have. Then you will decide how will that affect this physical property, this vapor pressure or whatever. And you also have to evaluate size. Because if you have a series of molecules that are all about the same size, and this could mean about the same size, could be anywhere from molar mass of 20 up to about 150, right? Those are all fairly small molecules. Then intermolecular forces matter the most. If you have a group of molecules that have the same intermolecular forces, then size matters. Okay, smaller things will evaporate more easily if they have the same intermolecular forces. Bigger things will evaporate more slowly if they have that same intermolecular forces. So a large hydrocarbon will evaporate more slowly than a small hydrocarbon. But you can't compare things of different size with different intermolecular force as well. Water is a really small molecule, but it has a super high boiling point. 100 degrees Celsius is really high for something that has a molar mass of 18. So when you look at that, you think, okay, so there it's the hydrogen bonding that's really determining that. But if you have a list of materials that all have the same intermolecular forces, size matters. I know sometimes people tell you it doesn't, but it does matter in chemistry. Size matters, right? So you have to think about molar mass of the molecule we're discussing. Now, let's look at that mathematically. We're going to look at the relationship between the vapor pressure and the temperature and the enthalpy of vaporization. But we have to do this mathematically, and it is a logarithmic function using the natural log function. So I want to quickly review how the logarithms are related and how you use your calculator to figure this out. Mostly, I want to make sure you know how to use the calculator you're going to use on the test. So we know that we have some number n that can be written as a to the b power. So a is the base and b is the exponent, or b is the logarithm, which is the power by which we raise the base to generate the number. So we could say log base a of n is equal to b. Now, we introduced this earlier when we talked about pH in the previous couple chapters back, and we were using common logs or base 10 logs. But we could work with anything. We're going to work in this unit with the natural logarithm, which is base e. So remember, in multiplication, logs are additive. If n is defined as a times b, then the log of n is the log of a plus the log of b. If n is defined as a divided by b, then the log of n is equal to the log of a minus the log of b. How many of you are used to separating logs to do your math and you're comfortable doing that? Nobody's raising their hand? Okay, the math people will show you how to do it that way. I'm going to show you a different way to deal with this because I think it's easier. When you separate the logs, you have to usually do two log functions. You have to take a log and you have to exponentiate. In my lazy way, you don't take a log. You leave it alone till the end, exponentiate, only have one log function, and I think that's easier. And if you have an exponent, the logs are multiplied. So if n is a to the b, then the log of n is the b times the log of a. Now, common log, we say log, but we're going to work with the natural logarithm. So please look at your small calculators and find the ln key, and the second function should be e to the x. Everybody find that? Okay, that's the key you're going to use. Now, every once in a while, your calculator will fail you. And it's not because it's the little calculator that you only paid $10 for. Even your $150 calculators will fail you in chemistry, because we will use some numbers that are so big the calculator can't handle it anymore for natural logarithms. So this is the way around it. The relationship between the natural log and the base 10 log is the natural log is 2.303 times the log base 10, or the common logarithm of n. So there may be a time that you need to remember that, and you just switch away from natural log, go to the base 10 log, and your calculator will work. Okay? It's kind of crazy the way the calculators are made, but if you know this relationship, you'll be able to salvage the situation. Your calculator will say overflow. That is not an acceptable answer on a chemistry test. Okay, you don't write overflow on there. You have to give me a number. So now, if we can take a log, we also have to go the other way and take the anti-log, or exponentiate. So if we know the log of n, or the natural log of n, and we want to find the n value, we take the exponent. Are you stretching, or you had a question? Okay. So for the natural log, we're going to use the e to the x key. And I just want you to plug these in and make sure that you know how the syntax works on your calculator. So what is the natural logarithm of 0.95? Some calculators, you push the ln button first. Some you type in the 0.95 and then push the button. Go ahead and work with yours to figure out how yours works. Did you get what I did? Negative 0.051293294. Is that what your calculator says? Yeah? Okay, so now when we think about the sig fig rules for logs, this number 0.95 has two significant figures. So the rule for logarithms is we report all the digits to the left of the decimal point, and then we report two digits to the right of the decimal. So even though that leading 0 is not considered a significant digit by us, that is the digit we report, and we get 0.05. That's all that we would report. Once we've reported that, we now only have one sig fig, and so we go forward in our calculations that way. Now try this one. What's the anti-log base e of 0.56? Using the natural log key, the second function, or the reciprocal function. Did you get what I did? So now, how would we report this, the anti-log of 0.56? Is it 1.75 when we're going backwards? No. Because this number has two decimals to the right of the decimal point, this number can have two sig figs. So we're going to stop in 2 sig figs, so we report 1.8. If I'm taking the logarithm of 1.8, I put 2 digits to the right of the decimal. When I'm taking the anti-log or exponentiating, I look at the 2 digits to the right of the decimal and I report 2 significant figures. So it's different rules when you go backwards.